Hey everyone, and welcome to this explainer. Today, we're setting out to completely demystify something that honestly often feels like pure magic. Just think for a second about the sheer, unimaginable volume of data we generate every single day. We're constantly sending texts, streaming high-definition videos, playing online games, loading complex web pages, the list goes on. But how does that human-readable data actually, physically travel across a computer network? It kind of feels invisible, right? Well, by the end of this, you'll see exactly how a simple human idea transforms and takes a journey right through the physical wire.
Okay, let's dive into this. We talk a lot about the cloud and global networks as if they're these totally abstract, invisible concepts just floating around in the sky somewhere. But this tangible physical Ethernet cable in someone's hand, that's the reality of the situation. To get a message from one side of the globe to the exact opposite side, it eventually has to travel down a physical medium just like this one. Even the most massive global cloud networks ultimately rely on thousands of miles of heavy, physical undersea cables laid right across the ocean floor. At the end of the day, it always comes back to the physical wire.
Here is our roadmap for the journey today. We'll start with the basics of propagation. Move on to binary as a universal language. Explore how we encode text and graphics, see how those bits become physical signals, and finally, look at how we modulate carrier waves to send that data. Let's get started.
Section 1. The Basics of Propagation. Traveling down the medium. So, a signal is, at its very core, simply a disturbance in the media. Propagation is the term we use for how that disturbance physically travels down the transmission medium to reach its receiver. Think of it like throwing a heavy rock into a long, narrow pond. That initial splash you make, that's the signal. And the ripple moving across the water, that's the propagation. But there's a really vital rule here. If the pond is too long, those clear, distinct ripples will slowly fade and bounce until they degrade into random, choppy water before they ever reach the other side. In networking, if these propagation effects get too large, the receiver literally won't be able to read the signal at all. It's just going to be noise.
Section 2. Binary, the universal language. Encoding everything into bits. Computers store and process absolutely all their data in binary representations. Binary just means 2, meaning there are only ones and zeros, which we call bits. But you might be wondering, why binary? Why not use numbers 1 through 10 like we do every day? Well, it's because at a microscopic hardware level, computer processors are really just made up of billions of tiny electrical switches. And a switch can only be in one of two physical states, on or off, 1 or 0. Now, some data in networking is inherently binary already, so it doesn't need any further encoding, like a 48-bit Ethernet address or a 32-bit IP address. But for everything else, text, decimal numbers, graphics, human voice, all of that non-binary data must be strictly encoded into these ones and zeros first, just to speak the physical language of those hardware switches.
Section 3. Encoding text and graphics. Translating human ideas.
Now, what's really interesting here is how perfectly organized this translation is. We use something called ASCII, a traditional code to represent text data in binary for transmission. Standard ASCII uses 7 bits per character. If you do the math on that, 2 to the 7th power gives us exactly 128 possible characters. That's enough for all your keyboard keystrokes, including the shifted values. So a capital A maps exactly to the binary code 10000001. A digit 3 is 0110011. Basically, every keystroke is assigned a specific binary code sent within an 8-bit byte. ASCII was actually born way back in the 1960s for clunky mechanical teletype machines. If you compare that highly efficient 7-bit system to today, sending a single colorful modern emoji can require up to 32 bits of memory just to render correctly. The scale has completely changed, but the foundational math, it remains exactly the same.
Okay, text is relatively simple, but what about a graphic? Let's walk through the math. Imagine an image with a screen resolution of 1000 by 500. By today's standards, that's actually a very low-resolution image, way less than standard high definition. But let's see just how much data it holds. Step 1. Multiply those dimensions together, and you get 500,000 pixels per screen. Step 2. We need colors. If we use 8 bits for each of our 3 base colors, red, green, and blue, that gives us 24 bits per pixel. So for step 3, we simply multiply our 500,000 pixels by 24 bits per pixel. And that brings us to 12 million. It's just an awe-inspiring scale. That single, tiny, relatively simple, low-resolution image requires 12 million bits, or 1.5 million bytes, just to be encoded on a single screen.
Imagine the math for a 4K movie streaming to your television at 60 frames per second. We are literally talking about billions upon billions of ones and zeros generated in the blink of an eye.
And this brilliantly illustrates a major dividing line in networking. All of that intense binary data encoding we just talked about, turning letters into ASCII or pixels into 12 million bits, happens at the application layer. You can kind of think of the application layer like writing a highly detailed letter and folding it neatly into an envelope. The message is completely ready, but it's not going anywhere just sitting there on your desk. To actually send it down the wire, we have to transition to the physical layer, and that is where signaling comes in. The physical layer is the postal truck actually driving down the highway, physically transporting your message to its final destination.
Section 4. Converting bits to signals, creating physical disturbances.
A surprisingly simple and elegant way to do this is binary signaling, like the on-off signaling used in optical fiber. It's wonderfully straightforward. During a clock cycle, the light is turned on for a 1 and the light is turned off for a 0. There are only 2 signaling states. You can picture it like 2 people standing on distant mountain peaks in the middle of the night using a remarkably bright flashlight to send Morse code to each other at the speed of light. This method is incredibly attractive because this brilliant simplicity gives the signal a massive relative immunity to errors as it travels across vast distances.
So, the crucial point here is how we separate these states in time. Think about our flashlight on the mountain. If the sender leaves the light turned on for 3 whole seconds, how on earth does the receiver know if that was one really long one or 3 separate ones sent back to back? They need a synchronized clock. We use vertical lines in our signaling diagrams to separate these opportunities to identify a 1 or a 0 from one another. The proper name for this single signaling event, this critical, perfectly synchronized timed opportunity, is a baud. The baud rate ensures both the sender and receiver totally agree on exactly how long a single bit is supposed to last.
Section 5. Modulating the carrier wave, altering signals to send data.
Now, not all cables use simple pulses of light. Many use electric signals or radio waves. And when we need different types of signaling, we actually have to manipulate a continuous physical wave itself, a process called modulation. There are exactly 3 properties of a wave that we can alter or modulate to carry our 1s and 0s. First up is amplitude, which results in amplitude shift keying, or ASK. Amplitude is the absolute value of the wave's highest intensity, usually measured in volts for electric signals. If you think about a sound wave, changing the amplitude is quite literally just like turning the volume up or down. Second is frequency, leading to frequency shift keying, or FSK. Frequency is the number of periods or cycles completed in 1 second, measured in hertz. Going back to our sound analogy, changing the frequency is like changing the pitch of a singer's voice from high to low. And third, we can alter the phase of the wave, known as phase shift keying, or PSK. By shifting these physical properties back and forth, essentially adjusting the volume or the pitch of the electrical wave, we successfully send our binary data zooming down the line.
Which brings us to the end of our explainer. But before we go, I really want to leave you with this thought. We calculated earlier that encoding just a single low-resolution image took 12 million bits. That means 12 million perfectly synchronized time signaling events, 12 million bauds, must flawlessly cross the physical wire just to load that single picture. Think about the high-definition videos you stream, the video calls you make, and the gigabytes of data you download every single day. How many billions of micro-disturbances are perfectly propagating down your network cable right this very second? It really is an incredible, almost unbelievable piece of science happening right in front of us every day. Keep learning, and I'll catch you in the next explainer.